Within the previous assessment of Latvian scientific institutions, Institute of Solid-State Physics, University of Latvia was evaluated in 5 categories. 2 of them had a rating 5, excellent, and the remaining 3 are rated as good. The category Research Environment and Infrastructure was among the 3 with rating 4. Therefore, infrastructure development became one of the priorities of our strategy. The basis of intensive infrastructure uprise was the Institute's ability to allocate more than 20 million euros from different sources. Raised funds were spent in 2 directions. Firstly, about 3 million euros has been invested in renovation of laboratories, offices and shared facilities. I would like to highlight that it is very important for us to create not only a technologically appropriate environment, but also comfortable and aesthetically pleasing conditions for both laboratories and offices. This also applies to renovated lobbies, corridors, stairs and elevators. Currently I am in one of the shared facilities in the room for lunching and relaxing. Of course, the most important are the laboratories of the Institute, half of which have been rebuilt, including 680 square meters of them converted into clean rooms. Secondly, more than 18 million was spent in purchase of research and technological equipment. All of them are installed in renovated facilities. We will continue a virtual tour with the newly established spectroscopy laboratory. My colleague Anatoly Sharakovskis will tell you about premium spectroscopy tools available at ISSP.
The Laboratory of Spectroscopy is the largest laboratory at the Institute, gathering roughly 40 employees, 14 of whom are scientists, others students and technicians. In recent years, the laboratory has been upgraded with scientific equipment, satisfying the demand from other laboratories at the Institute, other academic institutions in Latvia, as well as serving industrial needs locally and internationally. The unique strength of the laboratory is that it brings together various pieces of state-of-the-art spectroscopic equipment within a hand's reach. The laboratory operates in the open access regime, meaning that any laboratory from the Institute has a free access to the equipment and highly educated staff. For general characterization of the luminescence Edinburgh instruments, spectrometer is used. It allows a wide range of spectroscopic measurements, including luminescence spectra, luminescence excitation spectra, and luminescence decay kinetics measurements. Using an integrating sphere, the photoluminescence quantum yield measurements can be performed. The spectrometer is widely used by different laboratories at the Institute, especially by projects studying materials actual for organic light-emitting diodes, materials and devices. More specific spectroscopic equipment present in the laboratory involves wavelength tunable pulsed laser systems working in the nanosecond and picosecond range. The nanosecond pulsed laser system here is tunable from UV to infrared region and is equipped with closed cycle helium cryostat for the measurements at low temperatures. It is highly popular among different groups at the Institute and is mostly used in academic research. The picosecond laser system, also wide-range tunable from UV to infrared, has a detection system based on streak camera from CAMART², thus allowing to perform decay kinetics measurements in sub-nanosecond time domain. Being a member of crystal clear collaboration at CERN, the Institute is involved in the research of scintillator materials for the radiation detectors, where fast decay kinetics measurements are highly important. This is the Laboratory of Vibration Spectroscopy, and we have Fourier transformation infrared spectrometer here from Brugge, which is one of the most powerful benchtop vacuum spectrometers available. Its spectral range is from 10,000 reciprocal centimeters down to 10 reciprocal centimeters. Currently it is in the process of upgrade to include bolometer, thus extending the measurement limits and sensitivity further in the terahertz region. It is also equipped with microscope, allowing for measurements on microscopic scale. This spectrometer is used for academic purposes as well as industrial partners, namely, it is used for detection of ultra-low concentration of impurities in semiconductors by a local company producing solar-grade silicon. The other equipment, also present here in this laboratory, is Raman Spectrometer. It is a confocal Raman Spectrometer equipped with confocal microscope, 3 lasers, and 3 monochromators, thus ensuring excellent signal-to-noise ratio, sensitivity and resolution. It is also broadly used by different laboratories at the Institute for material characterization, as well as 2 local companies producing optical fibers for the characterization of their products. The Institute has a long tradition of research done on the radiation defects. One of the techniques that is extensively used to identify such defects is electron paramagnetic resonance. It is a non-destructive spectroscopic technique for the identification and analysis of paramagnetic species in solids. The spectrometer system at ISSP enables continuous wave X and Q band EPR, as well as X band electron nuclear double resonance measurements from 4 kelvins up to room temperature. Recently, this technique has been successfully applied to study formation and transformation of defects in radiation-resistant materials in Eurofusion enabling research project. Radiation defects can also be studied by thermo and optically stimulated luminescence. The laboratory is equipped with thermoluminescence optically stimulated luminescence reader from Freiberg Instruments, which is a versatile luminescence reader suited for research on the luminescence of materials and dosimetry needs. The system includes the integrated X-ray and beta-ray sources. Thermoluminescence measurements are possible with a versatile heater which can be programmed for linear or non-linear heating. The reader is extensively used by a number of projects involved in the research of personal dosimeters and dosimeters for medical needs. A great deal of industrial and academic research and characterization is performed on thin films. For this, Woolam spectroscopic ellipsometer is used. Spectroscopic ellipsometry is non-destructive and non-contact indirect optical measurement technique. It allows the characterization of a wide range of properties of a thin film, including optical constants, layer thickness, surface roughness, interface layers, composition, band gap, crystallinity, grading, anisotropy, and many others. The ellipsometer is mostly used by users for the characterization of thin films and coatings, particularly by a local company, Groglass, producer of anti-reflective coatings on glass. Finally, X-ray photoelectron spectroscopy, ultraviolet photoelectron spectroscopy machine from Thermoscientific. Quite often the chemical composition of material needs to be determined. Various techniques could be used for that, one of them XPS. The information is gained from a few nanometer depth, making the technique particularly suitable for the characterization of thin films and coatings. Equipped with argon gun, the spectrometer allows to obtain depth profile of heterostructured samples, for example, thin films with different layers. There is a strong demand for this equipment from many laboratories within the Institute and outside, as this is the only XPS machine in Latvia, and also from our industrial partners, Groglass, Sidrabe, Schaeffler, producing thin films and coatings.
Nowadays, computer modeling, or we like to say theoretical experiment, has become an important instrument for research. It represents an effective complement to experiments and in many cases provides important information on material properties and physical processes difficult to obtain in the experiments. Our institute is not an exception. Computer modeling at different scales down to nanometers are considered with best available programs and methods. For example, our researchers model properties of advanced materials using computational chemistry methods, molecular dynamics and Monte Carlo simulations, interpret X-ray absorption and magnetic resonance spectra of materials to understand their structure, calculate mesoscopic scale structural instabilities in ferroelectrics, and many other applications. To perform large-scale calculations, we have constructed in 2002 a Latvian supercluster, or so-called LASC. It is one of the most powerful supercomputers in the Baltic states, based on reliable multiprocess servers, connected via gigabit Ethernet networks and running under the Linux operating systems. Computational chemistry codes WASP, Crystal, Gaussian, CP2K, Quantum Espresso, and others are installed on the LASC. Many cell-written programs are also used on the LASC. In 2019, within the framework of CAMART² project, LASC was upgraded with new nodes with more than 2000 CPU cores, increasing computing power more than 10 times, up to 150 teraflops. 12 TB RAM memory and 127 TB total hard disk space are available on LASC. The system plays an important role in all research projects of the Institute related to the modeling of materials and predicting their properties, as well as theoretical analysis of experimental data. Currently, LASC is widely used by more than 60 users, including researchers and students. The system is important for raising the level of the Institute's research and provides support for collaborative activities with many other laboratories in the Institute and abroad. For example, modeling of water splitting processes and lattice dynamics in collaboration with Duisburg-Essen University, Germany, and Paul Scherrer Institute, Switzerland correspondingly, as well as solid-state ionic studies in the framework of long-standing collaboration with Max Planck Institute, Stuttgart, Germany, are strongly supported by LASC.
Laboratory of Chemical Technologies was established thanks to the financial support of CAMART² project. This laboratory can provide space and equipment for general and high-temperature synthesis, powder preparation, and characterization of wide variety of samples using modern equipment controlled with flexible software. The laboratory is currently mostly used for synthesis and characterization of proton-conducting polymer membranes, solving problems of luminescent upconverting nanomaterials, as well as researching and developing materials and methods for lithium-ion and sodium-ion batteries. Key research equipment includes particle characterization equipment, solid surface characterization equipment, pH meter, several ovens for high-temperature synthesis, as well as equipment for TGA and DSC. Accessible for everyone are also tabletop X-ray diffractometer and scanning electron microscope, with which, after a short training, anyone at the Institute can work with. I'm heading the Laboratory of Materials for Energy Harvesting and Storage, and I represent the battery research direction. We often use these facilities with currently 3 ongoing research projects. One of these is in collaboration with an industry partner. 2 more 3-year research projects are starting next year. We typically prepare battery electrodes in one of these fume hoods, after which we dry the electrodes in this vacuum oven. When the electrodes are dry, we assemble the battery cells and half cells in this argon-filled glove box. After that, we test the battery cells in the multi-channel battery tester that we also could purchase thanks to the CAMART² project.
Laboratory of Thin Films is one of the biggest laboratories of ISSP. Here we develop technologies for academic and industrial use. The 3 units you see here are constantly upgraded to the latest technologies, including HIPIMS, which is a high power impulse magnetron sputtering. This unit is designed for pure metal, oxide, hydride and nitride coatings using DC and pulse DC magnetron sputtering modes for solid and liquid targets and substrate temperature from room temperature to cryogenic temperatures. Currently, we are here performing projects which require transparent conductors. The additional features of this unit are liquid targets and temperature up to 800 degrees Celsius. Both devices are equipped with optical thickness control, time result plasma emission spectroscopy for process control, and substrate movement for coating uniformity. Currently, here we are performing gallium oxide multilayer coatings. The 3rd unit is devoted mostly for metal and oxide deposition. Currently, here we develop antiviral coatings for our state research program for COVID-19 cure. All devices have co-sputtering from 1 or 2 simultaneous targets. Our nanofabrication facilities, thin film multifunctional cluster tool and microscopy tools are located in our cleanroom facilities, which is the only academic nanofabrication facility in Latvia used by all laboratories of ISSP and external users from academia and industry. In our clean room, we have a set of workplaces for substrate cleaning, processing, etching and chemical synthesis, including glow boxes required, for example, for battery and OLED development projects. Here we see a multifunctional cluster tool with different techniques and sources for thin film and coating deposition. This is a good example of our cooperation with industry. It is produced by Sidrabe, who is developing industrial thin film and coating systems. It is used in many research and innovation projects to develop different devices like sensors and to develop new coatings and multi-coating structures. Important speciality of our clustered tool is deposition of organic materials, which we use in various photonic and electronic devices, starting from organic light-emitting diodes, ending with organic field effect transistors. As you see, our nanofabrication facilities combine various techniques, from atomic layer deposition to create precise coatings covering very complex textures to basic tools as spin coater. Our micro and nano lithography services are based on laser writer, allowing to create patterns with sub-micron precision, and electron beam lithography for nanometer precision. Our recent efforts are focused to create a nanophotonic platform, provide technology platform for National Quantum Technologies Initiative, develop microreactors used for chemical synthesis, and organ-on-a-chip systems where we cooperate with national and international biomedical research groups, including state research program against COVID-19. We are part of Euro Nanolab Consortium, where our specialization is to develop processes for organic materials.
In the Cleanrooms, there are 2 electron microscopes for material morphology and structure investigation. A dual-beam scanning electron microscope with focused ion beam, Tescan Lyra, is one of them. It is equipped with micromanipulators as well as optical and electrical inputs. Accordingly, it can also be used for nano-device measurements and nanofabrication. The second is transmission electron microscope Fate Techne, which has a higher accelerating voltage, up to 200 kV. Thus, high-resolution measurements are possible. Besides, selected area electron diffraction is used to study the crystalline structure. In addition to microscopy, the thickness and surface quality of films or photoresist can be determined by profilers. All of the mentioned scientific instruments are used in collaboration with most Latvian research institutions: University of Latvia, Riga Technical University, Latvian Institute of Organic Synthesis, and others. There is also an active scientific cooperation with international institutions. In addition, these devices are essential for several Latvian high-tech companies, such as Groglas, Sidrabe, Schaeffler, Keramoptek, etc. We are currently standing by our newcomer this year, the dual-beam microscope Helios. I am not afraid to say it out loud that it is the best and newest microscope of its kind in the Baltic Sea region. So what makes it so unique? The advantage of this microscope is that both the electron and ion columns work well at low accelerating voltage. The resolution of electron column is ensured by monochromator. This results in a higher image resolution in the fabrication of better quality samples for temp measurements. More than that, electron and ion lithography can be done by this microscope, but that is not all. There is a wide range of electron detectors that provide various information about sample just by imaging. Furthermore, this Helios also has an energy dispersive detector for chemical microanalysis and an electron backscatter diffraction detector for quantitative microstructural analysis. I want to highlight that one of the greatest things is the Fib tomography method, the serial milling and imaging of material slices, whereby the 3D volume visualization of the material is reconstructed. Nevertheless, the new equipment is also available for students and their research. For example, I started learning scanning electron microscopy 5 years ago, and now I am already using the new Helios for my doctoral dissertation. We are delighted to give students the opportunity to see world-class technologies and their capabilities, thereby inspiring the new generation of scientists.
And this is the end of our virtual excursion in premises of Institute of Solid-State Physics. Hopefully you get an insight about equipment and possibilities in our laboratories and have an understanding how we are developing in last times. Thank you and hope to see you next time in present and see how it looks in real life.